Hi, I'm Maya, and for my senior project, I'm studying how cooking is actually a lot of chemistry. So today I'm going to be taking you through a cooking video where I show you the step-by-step way to make pasta and red sauce and then chocolate chip cookies, but I'm going to explain the in-depth chemical processes of what's actually happening while your food is cooking. Without any further ado, let's get started. Alright, so I have my water right now and it's starting to boil. Now the boiling point of a liquid is the temperature at which the vapor pressure of the liquid is equal to the air pressure of the gas around the liquid, which in this case is the air under the lid of the pot. Now the water turns from its liquid to its gaseous state while it's boiling, and the internal temperature for water to boil has to be 100 degrees Celsius. When the transformation occurs, when liquid goes from its liquid state to its gaseous state, the intermolecular forces between water molecules have to be overcome and broken because molecules in the gaseous state have really negligible intermolecular forces. The enthalpy of vaporization is the amount of energy required to turn the water from liquid to gas, or the energy needed to overcome these intermolecular forces. Once the boiling point is reached, all of the energy goes towards turning the liquid to the gas, and none of it goes towards actually raising the temperature of the liquid once it reaches its boiling point. So once water reaches 100 degrees Celsius, it's not going to get hotter, it's just going to turn to gas. Now that our water is boiling, I'm going to add a little bit of table salt, which is just sodium chloride, to the boiling water. The salt is going to dissociate into positive sodium and negative chloride ions because it's an ionic solid. The addition of the salt will raise the boiling point of the water, which will give our water temperature a temperature higher than 100 degrees Celsius, which will help our pasta cook faster. The salt affects the boiling point of the water because, as we learned, water is a polar dipole molecule with a slightly positive and a slightly negative side. The positive hydrogen side of the water molecules will have an ion-dipole interaction with the negative chloride ions, and the negative oxygen side of the water molecule will have an ion-dipole interaction with the positive sodium ions. Because these are now more intermolecular forces in play, it takes more energy to break the bonds of the water and with the sodium chloride, and so therefore it's going to need more temperature to actually boil the solution. Alright, I'm now going to add some oil to our salty water. Oil is a fat, which means it's a non-polar substance, which means it won't form hydrogen or dipole bonds with the water. So it'll keep it separate from each other. When I add my pasta into the water, the oil will also keep that from sticking with itself because it won't be able to form dipole-dipole or polar bonds with each other, the pasta molecules, so they won't stick together. So here we go. And there's our pasta. We're just going to let that cook in the hot water for about 8 to 10 minutes. And how pasta actually cooks is that the water will rehydrate the pasta because it's absorbed into the starch molecules. The starch molecules in the pasta will then form into gel-like supersaturated solutions and help the pasta be more flexible and soft, which will appear cooked to us, and then it's more enjoyable to eat. Okay, so now we're making the sauce, and when I tasted it just a second ago, I noticed that it was just a little bit sour. This tells me that it's acidic. I also know that because it is tomato sauce and made of tomatoes, which contain citric acid, that it definitely is acidic. Now, I kind of want to mellow out that sour flavor, and so I can do this by slightly neutralizing the baking soda by adding something basic to this acidic substance. So that's where my baking soda comes in. I'm going to add just a little bit of baking soda, not enough to neutralize the entire pot of sauce, but to slightly mellow out that flavor and slightly raise the pH just a little bit. So when you see, it'll just slightly bubble when I add the sauce. Look at that. You can kind of hear it close to it. There's like a fizzing sound that comes, and you can see tiny bubbles, which are actually full of hydrogen gas. So the reaction for what we're seeing is now going to be on your screen. And there it is. And our sauce should just be a little bit more neutral now. Yeah, I'm tasting it and it actually is a lot less sour while it still has that awesome tomato flavor. So great, so there's our tomato sauce. Once my pasta's done, I'll add it on top. And so there we have it. We made pasta with red sauce. We learned how to slightly neutralize a weak acid and how salt affects the boiling point of water. All right, on to our next component. For dessert, we're going to have chocolate chip cookies. I chose to make these cookies for this project for two reasons. The first is that they're a pretty simple thing to bake, but I still get to explore the chemical processes that occur in the oven. But also, we used chocolate chip cookies in chemistry class to learn about the early atomic models. In 1897, English physicist J.J. Thomson discovered the electron, and revised the previous atomic theory of what an atom really looked like. He theorized that an atom is composed of electrons, tiny negatively charged particles, suspended in a mass of positively charged material. He likened the model to the British dessert plum pudding, but we were able to see the atoms as balls of chocolate chip cookie dough, where the chocolate chips are the electrons and the dough is the proton mass. This atomic model was later disproved, but the model did help us understand how protons and electrons balance each other's charges to create a neutrally charged model. The first step of making chocolate chip cookies is to mix all the ingredients evenly so that all the components are blending. First, we're going to add 2 sticks, so 1 cup of butter that is softened to room temperature, 3/4 cup of brown sugar, and 3/4 cup of white sugar. We're going to blend these up. We did that to make sure that the sugar is evenly distributed in all of the butter, because the sugar is one of the most important parts of cooking because of the caramelization process that occurs, which I'll explain later. Next, we're going to add 2 large eggs, which will act as the bonding agent in our cookies. We'll also add our vanilla extract for flavoring. And we'll give that a blend as well. All right. Now that our wet ingredients are all properly mixed together, we'll add 2 cups of flour, a teaspoon of salt, and possibly our most important ingredient, a teaspoon of baking soda. Let that stir. And what would chocolate chip cookies be without the chocolate chips? We'll add a good amount of those. A little more. Right, and stir one more time. All right, there we have it, our chocolate chip cookie dough, the early atomic model. All right, so I finished up getting my ingredients mixed together and I'm just balling up my cookies. The only chemical process that's really happened so far is that the sugar has slightly dissolved a little bit in some of my liquid materials, but nothing super big or effective for the actual cooking of the cookies has happened yet. All right, so I'm just putting my cookies into the oven. I preheated the oven to 350 degrees Fahrenheit, which is close to 200 degrees Celsius. This way, the cooking process can start immediately. The main process that actually starts the cooking of these cookies is the decomposition of baking soda. The equation for that should be on your screen now. But so the baking soda turns into the carbon dioxide gas, which will puff up the cookies and make them all nice and fluffy. Alright, so here we have our cookies fresh out of the oven. So hopefully it won't fall apart when we pick it up, and there it is. It's because of the egg that binds it together. When an egg cooks, the heat denatures the protein that the egg is made of, and long protein chains kind of sprawl out and then they get tangled together, which prevents them from falling apart and binds the flour and all of the other cookie components together. This is an almost irreversible process because it's so spontaneous based on its entropy and enthalpy, and so it would occur over enough time anyways if we left an egg out, like on the counter or something, but enough heat lets it happen over a span of 10 minutes is how long these cookies took to cook. So the hardness on the outside of the cookie is caused by the caramelization of the sugar. The sugar is sucrose, whose chemical formula is C12H22O11. When it caramelizes, or under enough heat, it reacts to form carmelanes, carmelanes, and carmelians. These substances have greater molar masses than sucrose, so they have more London dispersion intermolecular forces, which hold the molecules together and resist boiling and melting, so they can withstand higher temperatures than the sugar can. And therefore on the outside, where more heat has gotten to be able to find the surface, the cookie is darker and a little bit harder, like on the bottom where it was on the hot pan. They harden on the outside of the cookie, causing a brown color and a tougher outside, but we still get a nice soft center of the cookie. So there you have it. All the chemical reactions turned out, and these cookies are really good.